Profiles of the Future. Inquiry into the Limits of the Possible. Written by Arthur C. Clarke in 1962. Introduction. It is impossible to predict the future, and all attempts to do so in any detail appear ludicrous within a very few years. This book has a more realistic, yet at the same time more ambitious aim. It does not try to describe the future, but to describe the boundaries within which possible futures must lie. If we regard the ages which stretch ahead of us as an unmapped and unexplored country, what I am attempting to do is to survey its frontiers and to get some idea of its extent. The detailed geography of the interior must remain unknown until we reach it. With a few exceptions, I am limiting myself to a single aspect of the future, its technology, not the society that will be based upon it. This is not such a limitation as it may seem, for science will dominate the future even more than it dominates the present. Moreover, it is only in this field that prediction is at all possible. There are some general laws governing scientific extrapolation, as there are not, by Marx, in the case of politics or economics. I also believe, and hope, that politics and economics will cease to be as important in the future as they have been in the past. The time will come when most of our present controversies on these matters will seem as trivial or as meaningless as the theological debates in which the keenest minds of the Middle Ages dissipated their energies. Politics and economics are concerned with power and wealth, neither of which should be the primary, still less the exclusive, concern of full-grown men. Many writers have, of course, tried to describe the technological wonders of the future, with varying degrees of success. Jules Verne is the classic example, and one never likely to recur, for he was born at the unique moment of time and took full advantage of it. His life, from 1828 to 1905, neatly coincided with the rise of applied science. It almost exactly spans the interval between the first locomotive and the first aeroplane. Only one other man has exceeded Verne in the range and accuracy of his predictions. This is the American editor and inventor Hugo Gernsback, 1884 to 1967. Though his narrative gifts did not match the great Frenchman's, and his fame is therefore not of the same magnitude, Gernsback's indirect influence through his various magazines was comparable to Verne's. With few exceptions, scientists seem to make rather poor profits. This is surprising, for imagination is one of the first requirements of a good scientist. Yet, time and again, distinguished astronomers and physicists have made utter fools of themselves by declaring publicly that such and such a project was impossible. I shall have pleasure, in the next two chapters, in parading some splendid cautionary examples. The great problem, it seems, is finding a single person who combines sound scientific knowledge, or at least the feel for science, with a really flexible imagination. Verne qualified perfectly, and so did Wells, whenever he wished. But Wells, unlike Verne, was also a great literary artist, though he often pretended otherwise, and very sensibly did not allow himself to be shackled by mere facts, if they proved inconvenient. Having evoked the great shades of Verne and Wells, I would now go so far as to claim that only readers or writers of science fiction are really competent to discuss the possibilities of the future. It is no longer necessary, as it was a few years ago, to defend this genre from the attacks of ignorant or downright malicious critics. The finest work in the medium stands comparison with all but the very best fiction being published today. But we are not concerned here with the literary qualities of science fiction, only with its technical content. Over the last 30 years, tens of thousands of stories have explored all the conceivable, and most of the inconceivable, possibilities of the future. There are a few things that can happen that have not been described somewhere, in books or magazines. A critical, the adjective is important, reading of science fiction is essential training for anyone wishing to look more than 10 years ahead. The facts of the future can hardly be imagined ad initio by those who are unfamiliar with the fantasies of the past. This claim may produce indignation, especially among those second-rate scientists who sometimes make fun of science fiction. I have never known a first-rate one to do so, and I know several who write it. But the simple fact is that anyone with sufficient imagination to assess the future realistically would inevitably be attracted to this form of literature. I do not for a moment suggest that more than 1% of science fiction readers would be reliable prophets, but I do suggest that almost 100% of reliable prophets will be science fiction readers, or writers. As for my own qualifications for the job, I am content to let the published record speak for itself. Although, like all other propagandists for spaceflight, I overestimated the timescale and underestimated the cost. I am not in the least contrite about this error. Had we known back in the 1930s that it was going to cost billions of dollars to develop space vehicles, we should have been completely discouraged. No one could have believed in those days that such sums would ever be available. The speed with which space exploration is progressing would have seemed equally unlikely. When Hermann Oberth's pioneering book Die Rakete zu den Planeten was reviewed by Nature in 1924, that journal remarked with great daring, "In these days of unprecedented achievements, one cannot venture to suggest that Herr Oberth's ambitious scheme may not be realized before the human race is extinct. It has been realized, in large measure, before Professor Oberth is extinct." I can claim a slightly better record than Nature's reviewer. On glancing into my first novel, Prelude to Space, written in 1947, I am amused to see that though I scored a direct hit by giving 1959 as the date of the first moon rocket, I put manned satellites in 1970 and the landing on the moon in 1978. This seemed wildly optimistic to most people at the time, but now demonstrates my innate conservatism. A still better proof of this is provided by the fact that I see no attempt whatsoever in 1945 to patent the communication satellite. See Chapter 16. I couldn't have done so, as it happens, but at least I would have made the effort had I dreamed that the first experimental models would be operating while I was still in my 40s. In any event, this book is not concerned with timescales, only with ultimate goals. At the present rate of progress, it is impossible to imagine any technical feat that cannot be achieved, if it can be achieved at all, within the next 500 years. But for the purposes of this inquiry, it is all the same, whether the things discussed can be done in 10 years or in 10,000. My only concern is with what, not with when. For this reason, many of the ideas developed in this book will be mutually contradictory. To give an example, a really perfect system of communications would have an extremely inhibiting effect on transportation. Less obvious is the converse. If travel became instantaneous, would anyone bother to communicate? The future will have to choose between many competing superlatives. In such cases, I have described each possibility as if the other did not exist. In a similar manner, some chapters end on an optimistic note, others on a pessimistic. According to the point of view, both unlimited optimism and unlimited pessimism about the future are equally justified. In the final chapter, I have tried to reconcile both. It has been said that the art of living lies in knowing where to stop, and going a little further. In chapters 14 and 15, I have attempted to do this by discussing conceptions which are almost certainly not science fact, but science fantasy. Some people may regard a serious treatment of such ideas as invisibility and the fourth dimension as a waste of time, but in this context it is fully justified. It is as important to discover what cannot be done as what can be done, and it is sometimes considerably more amusing. While writing this introduction, I came across a review of a somewhat pedestrian Russian book about the 21st century. The distinguished British scientist writing the review found the work extremely reasonable and the author's extrapolations quite convincing. I hope this charge will not be leveled against me. If this book seems completely reasonable and all my extrapolations convincing, I shall not have succeeded in looking very far ahead. For the one fact about the future of which we can be certain is that it will be utterly fantastic. Chapter 1. Hazards of Prophecy, the Failure of Nerve. Before one attempts to set up in business as a prophet, it is instructive to see what success others have made of this dangerous occupation, and it is even more instructive to see where they have failed. With monotonous regularity, apparently competent men have laid down the law about what is technically possible or impossible and have been proved utterly wrong, sometimes while the ink was scarcely dry from their pens. On careful analysis, it appears that these debacles fall into two classes, which I will call failures of nerve and failures of imagination. The failure of nerve seems to be the more common. It occurs when, even given all the relevant facts, the would-be prophet cannot see that they point to an inescapable conclusion. Some of these failures are so ludicrous as to be almost unbelievable, and would form an interesting subject for psychological analysis. "They said it couldn't be done" is a phrase that occurs throughout the history of invention. I do not know if anyone has ever looked into the reasons why they said so, often with quite unnecessary vehemence. It is now impossible for us to recall the mental climate which existed when the first locomotives were being built, and critics gravely asserted that suffocation lay in wait for anyone who reached the awful speed of 30 miles an hour. It is equally difficult to believe that only 80 years ago, the idea of the domestic light was pooh-poohed by all the experts, with the exception of a 31-year-old American inventor named Thomas Alva Edison. When gas securities nosedived in 1878 because Edison, already a formidable figure with the phonograph and the carbon microphone to his credit, announced that he was working on the incandescent lamp, the British Parliament set up a committee to look into the matter. Westminster can beat Washington hands down at this game. The distinguished witnesses reported, to the relief of the gas companies, that Edison's ideas were good enough for our transatlantic friends, but unworthy of the attention of practical or scientific men. And Sir William Preece, Engineer-in-Chief of the British Post Office, roundly declared that subdivision of the electric light is an absolute ignis fatuus. One feels that the fatuousness was not in the ignis. The scientific absurdity being pilloried, be it noted, is not some wild and woolly dream like perpetual motion, but the humble little electric light bulb, which 3 generations of men have taken for granted, except when it burns out and leaves them in the dark. Yet altogether in this matter, Edison saw far beyond his contemporaries. He too in later life was guilty of the same short-sightedness that afflicted Preece and co., for he opposed the introduction of alternating current. The most famous, and perhaps the most instructive, failures of nerve have occurred in the fields of aero and astronautics. At the beginning of the 20th century, scientists were almost unanimous in declaring that heavier than air flight was impossible, and that anyone who attempted to build aeroplanes was a fool. The great American astronomer Simon Newcomb wrote a celebrated essay which concluded, "The demonstration that no possible combination of known substances, known forms of machinery, and known forms of force can be united in a practical machine by which men shall fly long distances through the air seems to the writer as complete as it is possible for the demonstration of any physical fact to be." Oddly enough, Newcomb was sufficiently broad-minded to admit that some wholly new discovery, he mentioned the neutralization of gravity, might make flight practical. One cannot, therefore, accuse him of lacking imagination. His error was in attempting to marshal the facts of aerodynamics when he did not understand that science. His failure of nerve lay in not realizing that the means of flight were already at hand. For Newcomb's article received wide publicity at just about the same time that the Wright brothers, not having a suitable anti-gravity device in their bicycle shop, were mounting a petrol engine on wings. When news of their success reached the astronomer, he was only momentarily taken aback. Flying machines might be a marginal possibility, he conceded, but they were certainly of no practical importance, for it was quite out of the question that they could carry the extra weight of a passenger as well as that of a pilot. Such refusal to face facts, which now seem so obvious, has continued throughout the history of aviation. Let me quote another astronomer, William H. Pickering, straightening out the uninformed public a few years after the first aeroplanes had started to fly. The popular mind often pictures gigantic flying machines speeding across the Atlantic and carrying innumerable passengers in a way analogous to our modern steamships. It seems safe to say that such ideas must be wholly visionary, and even if a machine could get across with one or two passengers, the expense would be prohibitive to any but the capitalist who could own his own yacht. Another popular fallacy is to expect enormous speed to be obtained. It must be remembered that the resistance of the air increases as the square of the speed and the work as the cube. If with 30 HP we can now attain a speed of 40 miles per hour, then in order to reach a speed of 100 miles per hour, we must use a motor capable of 470 horsepower. It is clear that with our present devices there is no hope of competing for racing speed with either our locomotives or our automobiles. It so happens that most of his fellow astronomers considered Pickering far too imaginative. He was prone to see vegetation and even evidence for insect life on the moon. I am glad to say that by the time he died in 1938, at the ripe age of 80, Professor Pickering had seen aeroplanes traveling at 400 miles per hour and carrying considerably more than one or two passengers. Closer to the present, the opening of the space age has produced a mass vindication and refutation of prophecies on a scale and at a speed never before witnessed. Having taken some part in this myself, and being no more immune than the next man to the pleasures of saying, "I told you so," I would like to recall a few of the statements about spaceflight that have been made by prominent scientists in the past. It is necessary for someone to do this and to jog the remarkably selective memories of the pessimists. The speed at which those who once declaimed it's impossible can switch to "I said it could be done all the time" is really astounding. As far as the general public is concerned, the idea of spaceflight as a serious possibility first appeared on the horizon in the 1920s, largely as a result of newspaper reports of the work of the American Robert Goddard and the Romanian Hermann Oberth, the much earlier studies of Tchaikovsky in Russia then being almost unknown outside his own country. When the ideas of Goddard and Oberth, usually distorted by the press, filtered through to the scientific world, they were received with hoots of derision. For a sample of the kind of criticism the pioneers of astronautics had to face, I present this masterpiece from a paper published by one Professor A.W. Bickerton in 1926. It should be read carefully, for as an example of arrogant ignorance, it would be very hard to beat. This foolish idea of shooting at the moon is an example of the absurd length to which vicious specialization will carry scientists working in thought-tight compartments. Let us critically examine the proposal. For a projectile entirely to escape the gravitation of the Earth, it needs a velocity of 7 miles a second. The thermal energy of a gram at this speed is 15,000 calories. The energy of our most violent explosive, nitroglycerin, is less than 1,500 calories per gram. Consequently, even had the explosive nothing to carry, it only has 1/10 of the energy necessary to escape the Earth. Hence, the proposition appears to be basically impossible. Indignant readers in the Colombo Public Library pointed angrily to the silence notices when I discovered this little gem. It is worth examining in some detail to see just where vicious specialization, if one may coin a phrase, led the professor so badly astray. His first error lies in the sentence, "the energy of our most violent explosive, nitroglycerin." One would have thought it obvious that energy, not violence, is what we want from a rocket fuel, and as a matter of fact, nitroglycerin and similar explosives contain much less energy, weight for weight, than such mixtures as kerosene and liquid oxygen. This had been very carefully pointed out by Tchaikovsky and Goddard years before. Bickerton's second error is much more culpable. Without mincing words, it is due to sheer stupidity. What of it, if nitroglycerin has only 1/10 of the energy necessary to escape the Earth? That merely means that you have to use at least 10 pounds of nitroglycerin to launch a single pound of payload. For the fuel itself has not got to escape from Earth. It can be all burned quite close to the planet, and as long as it imparts its energy to the payload, that is all that matters. When Lunik 2 lifted 33 years after Professor Bickerton said it was impossible, most of its several hundred tons of kerosene and liquid oxygen never got very far from Russia, but the half-ton payload reached the Mare Imbrium. As a comment to the above, I might add that Professor Bickerton, who was an active popularizer of science, numbered among his published books one with the title Perils of a Pioneer. Of all the perils that all pioneers must face, few are more disheartening than the Bickertons. Right through the 1930s and 1940s, eminent scientists continued to deride the rocket pioneers, when they bothered to notice them at all. Anyone who has access to a good college library can find, preserved for posterity in the dignified pages of the January 1941 Philosophical Magazine, an example specially interesting owing to the eminence of its author. It is a paper by the distinguished Canadian astronomer Professor J.W. Campbell of the University of Alberta, entitled Rocket Flight to the Moon, opening with a quotation from a 1938 Edmonton paper to the effect that rocket flight to the moon now seems less remote than television appeared 100 years ago. The professor then looks into the subject mathematically. After several pages of analysis, he arrives at the conclusion that it would require 1 million tons of takeoff weight to carry 1 pound of payload on the round trip. The correct figure for today's primitive fuels and technologies is very roughly 1 ton per pound. A depressing ratio, but hardly as bad as that calculated by the professor. Yet his mathematics was impeccable, so what went wrong? Merely his initial assumptions, which were hopelessly unrealistic. He chose a path for the rocket which was fantastically extravagant in energy, and he assumed that the use of an acceleration so low was that most of the fuel would be wasted at low altitudes, fighting the Earth's gravitational field. It was as if he had calculated the performance of an automobile when the brakes were on. No wonder that he concluded, while it is always dangerous to make a negative prediction, it would appear that the statement that rocket flight to the moon does not seem so remote as television did less than 100 years ago is over-optimistic. I am sure that when Philosophical Magazine subscribers read those words back in 1941, many of them thought, well, that should put those crazy rocket men in their place. Yet the correct results had been published by Tchaikovsky, Oberth, and Goddard years before, though the work of the first two would have been very hard to consult at the time. Goddard's paper, A Method of Reaching Extreme Altitudes, was already a classic, and it had been issued by that scarcely obscure body, the Smithsonian Institution. If Professor Campbell had only consulted it, or indeed any competent writer on the subject, there were some even in 1914, he would not have misled his readers and himself, and he would not have to put up with a rather sarcastic analysis of his paper by myself in the September 1948 issue of the Journal of the British Interplanetary Society, which caused him some pain on its appearance. If he happens to read these words, I apologize for my rudeness, but not for my criticism. The lesson to be learned from these examples is that one can never be repeated too often, and one that is seldom understood by laymen who have an almost superstitious awe of mathematics. But mathematics is only a tool, though an immensely powerful one. No equations, however impressive and complex, can arrive at the truth if the initial assumptions are incorrect. It is really quite amazing by what margins competent but conservative scientists and engineers can miss the mark when they start with the preconceived idea that what they are investigating is impossible. When this happens, the most well-informed men become blinded by their prejudices and are unable to see what lies directly ahead of them. What is even more incredible, they refuse to learn from experience. They will continue to make the same mistake over and over again. Some of my best friends are astronomers, and I am sorry to keep throwing stones at them, but they do seem to have an appalling record as prophets. If you will still doubt this, let me tell you a story so ironic that you might well accuse me of making it up, but I am not that much of a cynic. The facts are on file for anyone to check. Back in the dark ages of 1935, the founder of the British Interplanetary Society, P.E. Clarke, was rash enough to write the first book on astronautics published in England. His Rockets Through Space gave an, incidentally, highly entertaining account of the experiments that had been carried out by the German and American rocket pioneers, and their plans for such commonplaces of today as giant multi-stage boosters and satellites. Rather surprisingly, the staid scientific journal Nature reviewed the book in its issue from March 14, 1936, and summed up as follows. It must be said at once that the whole procedure sketched in the present volume presents difficulties of so fundamental a nature that we are forced to dismiss the notion as essentially impracticable, in spite of the author's insistent appeal to put aside prejudice and to recollect the supposed impossibility of heavier-than-air flight before it was actually accomplished. An analogy such as this may be misleading, and we believe it to be so in this case. Well, the whole world now knows just how misleading this analogy was, though the reviewer, identified only by the unusual initials RVDRW, was, of course, fully entitled to his opinion. Just 20 years later, after President Eisenhower had announced the United States satellite program, a new astronomer royal arrived in England to take up his appointment. The press asked him to give his views on spaceflight, and after 2 decades, Dr. Richard van der Wright-Woolley had seen no reason to change his mind. Space travel, he snorted, is utter bilge. The newspapers did not allow him to forget this when Sputnik 1 went up the very next year. Later, irony piled upon irony, Dr. Woolley became, by virtue of his position as Astronomer Royal, a leading member of the committee advising the British government on space research. The feelings of those who have been trying for a generation to get the United Kingdom interested in space can well be imagined. Even those who suggested that rockets might be used for more modest, though much more reprehensible purposes, were overruled by the scientific authorities, except in Germany and Russia. When the existence of the 200-mile range V2 was disclosed to an astonished world, there was considerable speculation about intercontinental missiles. This was firmly squashed by Dr. Vannevar Bush, the civilian general of the U.S. scientific war effort, in evidence before a Senate committee on 3 December 1945. Listen. There has been a great deal said about 3,000-mile high-angle rockets. In my opinion, such a thing is impossible for many years. The people who have been writing these things that annoy me have been talking about a 3,000-mile high-angle rocket shot from one continent to another, carrying an atomic bomb and so directed to be a precise weapon which would land exactly on a certain target, such as a city. I say technically, I don't think anyone in the world knows how to do such a thing, and I feel confident that it will not be done for a very long period of time to come. I think we can leave that out of our thinking. I wish that the American public would leave that out of their thinking. A few months earlier, in May 1945, Prime Minister Churchill's scientific advisor, Lord Cherwell, had expressed similar views in a House of Lords debate. This was only to be expected, for Cherwell was an extremely conservative and opinionated scientist who had advised the government that the V2 itself was only a propaganda rumour. In the May 1945 debate on defence, Lord Cherwell impressed his peers by a dazzling display of mental arithmetic, by which he correctly concluded that a very long-range rocket must consist of more than 90% fuel, and thus would have a negligible payload. The conclusion he let his listeners draw from this was that such a device would be wholly impracticable. That was true enough in the spring of 1945, but it was no longer true in the summer. One astonishing feature of the House of Lords debate is the casual way in which much too well-informed peers used the phrase atomic bomb, at a time when this was the best-kept secret of the war. The Alamogordo test was still 2 months in the future. Security must have been horrified, and Lord Cherwell, who of course knew all too well about the Manhattan Project, was quite justified in telling his inquisitive colleagues not to believe everything they heard, even though in this case it happened to be perfectly true. When Dr. Bush spoke to the Senate committee in December of the same year, the only important secret about the atomic bomb was that it weighed 5 tons. Anyone could then work out in his head, as Lord Cherwell had done, that a rocket to deliver it across intercontinental ranges would have to weigh about 200 tons, as against the mere 14 tons of the then awe-inspiring V2. The outcome was the greatest failure of nerve in all history, which changed the future of the world, indeed of many worlds. Faced with the same facts and the same calculations, American and Russian technology took 2 separate roads. The Pentagon, accountable to the taxpayer, virtually abandoned long-range rockets for almost half a decade, until the development of thermonuclear bombs made it possible to build warheads 5 times lighter, yet 50 times more powerful than the amusing firecracker that was dropped on Hiroshima. The Russians had no such inhibitions. Faced with the need for a 200-ton rocket, they went right ahead and built it. By the time it was perfected, it was no longer required for military purposes, for Soviet physicists had bypassed the United States billion-dollar tritium bomb cul-de-sac and gone straight to the far cheaper lithium bomb. Having backed the wrong horse in rocketry, the Russians then entered it at a much more important event, and won the race into space. Of the many lessons to be drawn from this slice of recent history, the one that I wish to emphasize is this. Anything that is theoretically possible will be achieved in practice, no matter what the technical difficulties, if it is desired greatly enough. It is no argument against any project to say the idea's fantastic. Most of the things that have happened in the last 50 years have been fantastic, and it is only by assuming that they will continue to be so that we have any hope of anticipating the future. To do this, to avoid that failure of nerve for which history extracts so merciless a penalty, we must have the courage to follow all technical extrapolations to their logical conclusion. Yet even this is not enough, as I shall now demonstrate. To predict the future, we need logic, but we also need faith and imagination, which can sometimes defy logic itself. Chapter 2. Hazards of Prophecy. The Failure of Imagination. In the last chapter, I suggested that many of the negative statements about scientific possibilities and the gross failures of past prophets to predict what lay immediately ahead of them could be described as failures of nerve. All the basic facts of aeronautics were available in the writings of Cayley, Stringfellow, Chanute, and others. When Simon Newcomb proved that flight was impossible, he simply lacked the courage to face those facts. All the fundamental equations and principles of space travel had been worked out by Tchaikovsky, Goddard, and Oberth for years, often decades, when distinguished scientists were making fun of would-be astronauts. Here again, the failure to appreciate the facts was not so much intellectual as moral. The critics did not have the courage that their scientific convictions would have given them. They could not believe the truth even when it was spelled out before their eyes, in their own language of mathematics. We all know this type of cowardice, because at some time or other, we all exhibit it. The second type of prophetic failure is less blameworthy and more interesting. It arises when all the available facts are appreciated and marshaled correctly, but when the really vital facts are still undiscovered and the possibility of their existence is not admitted. A famous example of this is provided by the philosopher Auguste Comte, who in his Cause de philosophie positive, 1835, attempted to define the limits within which scientific knowledge must lie. In his chapter on astronomy, Book 2, Chapter 1, he wrote these words concerning the heavenly bodies. We see how we may determine their forms, their distances, their bulks, their motions, but we can never know anything of their chemical or mineralogical structure, and much less that of organized beings living on their surface. We must always keep carefully apart the idea of the solar system and that of the universe, and be always assured that our only true interest is in the former. Within this boundary alone is astronomy the supreme and positive science that we have determined it to be. The stars serve us scientifically only as providing positions with which we may compare the interior movements of our system. In other words, Comte decided that the stars could never be more than celestial reference points, of no intrinsic concern to the astronomer. Only in the case of the planets could we hope for any definite knowledge, and even that knowledge would be limited to geometry and dynamics. Comte would probably have decided that such a science as astrophysics was a priori impossible. Yet within half a century of his death, almost the whole of astronomy was astrophysics, and very few professional astronomers had much interest in the planets. Comte's assertion had been utterly refuted by the invention of the spectroscope, which not only revealed the chemical structure of the heavenly bodies, but has now told us far more about the distant stars than we know of our planetary neighbors. Comte cannot be blamed for not imagining the spectroscope. No one could have imagined it, or the still more sophisticated instruments that have now joined it in the astronomer's armory. But he provides a warning that should always be borne in mind. Even things that are undoubtedly impossible with existing or foreseeable techniques may prove to be as easy as the result of new scientific breakthroughs. From their very nature, these breakthroughs can never be anticipated, but they have enabled us to bypass so many insuperable obstacles in the past that no picture of the future can hope to be valid if it ignores them. Another celebrated failure of imagination was that persisted in by Lord Rutherford, who more than any other man laid bare the internal structure of the atom. Rutherford frequently made fun of those sensation mongers who predicted that we would one day be able to harness the energy locked up in matter. Yet only 5 years after his death in 1937, the first chain reaction was started in Chicago. What Rutherford, for all his wonderful insight, had failed to take into account was that a nuclear reaction might be discovered that would release more energy than required to start it. To liberate the energy of matter, what was wanted was a nuclear fire, analogous to chemical combustion, and the fission of uranium provided this. Once that was discovered, the harnessing of atomic energy was inevitable, though without the pressures of war, it might well have taken the better part of a century. The example of Lord Rutherford demonstrates that it is not the man who knows most about a subject, and is the acknowledged master of his field, who can give the most reliable pointers to the future. Too great a burden of knowledge can clog the wheels of imagination. I have tried to embody this fact of observation in Clarke's law, which may be formulated as follows. When a distinguished but elderly scientist states that something is possible, he is almost certainly right. When he states that something is impossible, he is very probably wrong. Perhaps the adjective elderly requires definition. In physics, mathematics, and astronautics, it means over 30. In the other disciplines, senile decay is sometimes postponed to the 40s. There are, of course, glorious exceptions, but as every researcher just out of college knows, scientists of over 50 are good for nothing but board meetings, and should at all costs be kept out of the laboratory. Too much imagination is much rarer than too little. When it occurs, it usually involves the unfortunate possessor in frustration and failure, unless he is sensible enough to merely write about his ideas, and not attempt their realization. In the first category, we find all the science fiction authors, historians of the future, creators of utopias, then the two Bacons, Roger and Francis. Friar Roger, circa 1214 to 1292, imagined optical instruments and mechanically propelled boats and flying machines, devices far beyond the existing or even foreseeable technology of his time. It is hard to believe that these words were written in the 13th century. Instruments may be made by which the largest ships, with only one man guiding them, will be carried with greater velocity than if they were full of sailors. Chariots may be constructed that will move with incredible rapidity without the help of animals. Instruments of flying may be formed in which a man, sitting at ease and meditating in any subject, may beat the air with these artificial wings after the manner of birds, as also machines which will enable men to walk at the bottom of the seas. This passage is a triumph of imagination over hard fact. Everything in it has come true, yet at the time it was written, it was more an act of faith than of logic. It is probable that all long-range prediction, if it is to be accurate, must be of this nature. The real future is not logically foreseeable. A splendid example of a man whose imagination ran ahead of his age was the English mathematician Charles Babbage, 1792 to 1871. As long ago as 1819, Babbage had worked out the principles underlying automatic computing machines. He realized that all mathematical calculations could be broken down into a series of step-by-step operations, which could, in theory, be carried out by a machine. With the aid of a government grant, which eventually totaled £17,000, a very substantial sum of money in the 1820s, he started to build his analytical engine. Though he devoted the rest of his life, and much of his private fortune, to the project, Babbage was unable to complete the machine. What defeated him was the fact that precision engineering of the standard he needed to build his cogs and gears simply did not exist at the time. By his efforts, he helped create the machine tool industry, so that in the long run the government got back very much more than its £17,000, and today it would be perfectly straightforward matter to complete Babbage's computer, which now stands as one of the most fascinating exhibits in the London Science Museum. In his own lifetime, however, Babbage was only able to demonstrate the operation of a relatively small portion of the complete machine. A dozen years after his death, his biographer wrote, "This extraordinary monument of theoretical genius accordingly remains, and doubtless will forever remain, a theoretical possibility." There is not much left of that doubtless today. At this moment, there are thousands of computers working on the principles that Babbage clearly outlined more than a century ago, but with a range and a speed of which he could never have dreamed. For what makes the case of Charles Babbage so interesting and so pathetic is that he was not one but two technological revolutions ahead of his time. Had the precision tool industry existed in 1820, he could have built his analytical engine, and it would have worked much faster than a human computer, but very slowly by the standards of today. For it would have been geared, literally, to the speed with which cogs and shafts and cams and ratchets can operate. Automatic calculating machines could not come into their own until electronics made possible speeds of operation thousands and millions of times swifter than could be achieved with purely mechanical devices. This level of technology was reached in the 1940s, and Babbage was then promptly vindicated. His failure was not one of imagination, it lay in being born 100 years too soon. One can only prepare for the unpredictable by trying to keep an open and unprejudiced mind, a feat which is extremely difficult to achieve, even with the best will in the world. Indeed, a completely open mind would be an empty one, and freedom from all prejudices and preconceptions is an unattainable ideal. Yet there is one form of mental exercise that can provide good basic training for would-be prophets. Anyone who wishes to cope with the future should travel back in imagination a single lifetime, say to 1900, and ask himself just how much of today's technology would be, not merely incredible, but incomprehensible to the keenest scientific brains of that time. 1900 is a good round date to choose because it was just about then that all hell seemed to break loose in science. As J.B. Conant has put it, somewhere about 1900, science took a totally unexpected turn. There had previously been several revolutionary theories and more than one epoch-making discovery in the history of science, but what occurred between 1900 and, say, 1930 was something different. It was a failure of a general prediction about what might be confidently expected from experimentation. P.W. Bridgman has put it even more strongly. The physicist has passed through an intellectual crisis forced by the discovery of experimental facts of a sort which he had not previously envisaged, and which he would not have thought possible. The collapse of classical science actually began with Rontgen's discovery of X-rays in 1895. Here was the first clear indication, in a form that anyone could appreciate, that the common-sense picture of the universe was not sensible after all. X-rays, the very name reflects the bafflement of scientist and layman alike, could travel through solid matter, like light through a sheet of glass. No one had ever imagined or predicted such a thing, that one would be able to peer into the interior of a human body, and thereby revolutionize medicine and surgery, was something that the most daring prophet had never suggested. The discovery of X-rays was the first great breakthrough into the realms where the human mind had ever ventured before, yet it gave scarcely a hint of still more astonishing developments to come: radioactivity, the internal structure of the atom, relativity, the quantum theory, the uncertainty principle. As a result of this, the inventions and technical devices of our modern world can be divided into two sharply defined classes. On the one hand, there are those machines whose working would have been fully understood by any of the great thinkers of the past. On the other, there are those that would be utterly baffling to the finest minds of antiquity. And not merely of antiquity. There are devices now coming into use that might well have driven Edison or Marconi insane had they tried to fathom their operation. Let me give some examples to emphasize this point. If you showed a modern diesel engine, an automobile, a steam turbine, or a helicopter to Benjamin Franklin, Galileo, Leonardo da Vinci, and Archimedes, a list spanning 2,000 years of time, not one of them would have had any difficulty in understanding how these machines worked. Leonardo, in fact, would recognize several from his notebooks. All four men would be astonished at the materials and the workmanship, which would have seemed magical in its precision. But once they had got over that surprise, they would have felt quite at home, so long as they didn't delve too deeply into the auxiliary control and electrical systems. But now suppose they were confronted by a television set, an electronic computer, a nuclear reactor, a radar installation. Quite apart from the complexity of these devices, the individual elements of which they are composed would be incomprehensible to any man born before this century. Whatever his degree of education or intelligence, he would not possess the mental framework that could accommodate electron beams, transistors, atomic fusion, waveguides, and cathode ray tubes. The difficulty, let me repeat, is not one of complexity. Some of the simplest modern devices would be the most difficult to explain. A particularly good example is given by the atomic bomb, at least the early models. What could be simpler than banging two lumps of metal together? Yet, how could one explain to Archimedes that the result could be more devastation than produced by all the wars between the Trojans and the Greeks? Suppose you went to any scientist up to the late 19th century and told him, here are two pieces of a substance called uranium-235. If you hold them apart, nothing will happen. But if you bring them together suddenly, you will liberate as much energy as you could obtain from burning 10,000 tons of coal. No matter how far-sighted and imaginative he might be, your pre-20th century scientist would have said, "What utter nonsense. That's magic, not science. Such things can't happen in the real world." Around 1890, when the foundations of physics and thermodynamics had, it seemed, been securely laid, he would have told you exactly why it was nonsense. Energy cannot be created out of nowhere, he might have said. It has to come from chemical reactions, electrical batteries, coiled springs, compressed gas, spinning flywheels, or some other clearly defined source. All such sources are ruled out in this case, and even if they were not, the energy output you mention is absurd. Why, it is 1,000,000 times more available from the most powerful chemical reaction. The fascinating thing about this particular example is that even when the existence of atomic energy was fully appreciated, say right up to 1940, almost all scientists would still have laughed at the idea of liberating it by bringing pieces of metal together. Those who believed that the energy of the nucleus could ever be released almost certainly pictured complicated electrical devices, atom smashers, and so forth, doing the job. In the long run, this will probably be the case. It seems that we will need such machines to fuse hydrogen nuclei on the industrial scale, but once again, who knows? The wholly unexpected discovery of uranium fission in 1938 made possible such absurdly simple, in principle if not in practice, devices as the atomic bomb and the nuclear chain reactor. No scientists could ever have predicted them. If he had, all his colleagues would have laughed at him. It is highly instructive and stimulating to the imagination to make a list of the inventions and discoveries that have been anticipated and those that have not. Here is my attempt to do so. All the items on the left have already been achieved or discovered, and all have an element of the unexpected or the downright astonishing about them. To the best of my knowledge, not one was foreseen very much in advance of the moment of revelation. On the right, however, are concepts that have been around for hundreds or thousands of years. Some have been achieved, others will be achieved, others may be impossible. But which? The unexpected. X-rays, nuclear energy, radio, TV, electronics, photography, sound recording, quantum mechanics, relativity, transistors, masers, lasers, superconductors, superfluids, atomic clocks, Mossbauer effect, determining composition of celestial bodies, dating the past with carbon-14, detecting invisible planets, the ionosphere, Van Allen belts, telepathy. The expected. Automobiles, flying machines, steam engines, submarines, spaceships, telephones, robots, death rays, transmutation, artificial life, immortality, invisibility, levitation, teleportation, communication with the dead, observing the past and future. The right-hand list is deliberately provocative. It includes sheer fantasy, as well as serious scientific speculation. But the only way of discovering the limits of the possible is to venture a little way past them into the impossible. As 3 laws were good enough for Newton, I have modestly decided to stop there. In the chapters that follow, this is exactly what I hope to do, yet I am very much afraid that from time to time, I too will exhibit failure of imagination, if not failure of nerve. For as I glance down the left-hand column, I am aware of a few items which, only 10 years ago, I would have thought were impossible. Chapter 3. The future of transport. Most of the energy expended in the history of the world has been used to move things from one place to another. For thousands upon thousands of years, the rate of movement was very low, less than 2 or 3 miles per hour, the pace of a walking man. Even the domestication of the horse did not raise this figure appreciably, for although a racehorse can exceed 40 miles an hour for very short periods, the main use of the horse has always been as a slow-moving beast of burden and a hauler of vehicles. The fastest of these, the stagecoaches immortalized by Dickens, could seldom have traveled more than 10 miles an hour on the roads that existed before the 19th century. For almost the whole of human history and prehistory, therefore, men's thoughts and their ways of life have been restricted to the tiny band of the speed system between 1 and 10 miles per hour. Yet, within the span of a few generations, the velocity of travel has multiplied 100-fold. Indeed, there are good grounds for thinking that the acceleration that has taken place around the mid-20th century will never again be matched. Speed, however, is not the only criterion of transport, and there are times when it is positively undesirable, especially if it conflicts with safety, comfort, or economics. As far as transportation at ground level is concerned, we may well have reached, if not passed, the practical limit of speed, and future improvements must lie in other directions. No one wants to travel down Oxford Street at the velocity of sound, but many Londoners would be very happy if they could always be sure of doing so at the speed of a stagecoach. There are many ways of classifying methods of transportation, the most obvious being by media, land, sea, air, or space. But these divisions are becoming more and more arbitrary, for there are vehicles that operate equally efficiently in 2 or more of them. For the present purpose, a scheme based on distance is the most convenient. On our 8,000-mile diameter, only 4 ranges are involved. 1 to 10 mile short range, such as foot, horse, bicycle. A 10 to 100 mile range, such a short range, such as car, bus, rail, and boat. A 100 to 1,000 medium range, like a car, bus, rail, or aeroplane. A 1,000 to 10,000 mile intercontinental range, like rail, aeroplane, ships, rockets, submarines. In the first category, very short ranges, only police, doctors, and firemen have any need to travel at over 50 miles an hour, or any right to inflict such speeds on the community. For this range, I would suggest that the ideal means of individual transportation is the motor scooter, or the very small bubble car. Indeed, I would like to be thoroughly reactionary and suggest that the almost obsolete habit of walking still has much to recommend it in terms of physical health, mental well-being, and frequently speed, as anyone who has ever been caught in a big city traffic jam will admit. Perhaps the only excuse for not walking, when short distances are involved, is the weather, and even this excuse will eventually vanish. In the cities, of course, the weather will be fully controlled before another century has passed. And outside them, even if we cannot control it, we will certainly be able to predict it and make plans accordingly. While we are in this backwards-looking mood, let me make an even more startling suggestion. The best personal transport vehicle man has ever possessed, where only short ranges are concerned and the weather is good, is the horse. It is self-steering, self-reproducing, never goes out of style, and only a double-decker bus gives a comparable view of the scenery. I admit that there are some disadvantages. Horses are expensive to maintain, prone to embarrassing behavior, and are not really very bright. But these are not fundamental limitations, for one day we will be able to increase the intelligences of our domestic animals, or evolve wholly new ones with much higher IQ than any existing now. When this happens, much of the short-range transport, at least in rural areas, may once again be non-mechanical, though not necessarily equine. The horse may not turn out to be the best choice in the long run. Something like a compact elephant might be more preferable because of its dexterity. It is only the quadruped that can carry out delicate handling operations while remaining a quadruped. In any event, it should be herbivorous. Carnivores are much too expensive to feed, and might take a fancy to their riders. What I am suggesting is for an animal large enough to carry a man at a fair speed, and intelligent enough to forage for itself without creating a nuisance or getting lost. It would report for duty at regular times, or when summoned over a radio command by circuit, and it would carry out many simple errands by itself without direct human supervision. It seems to me that there would be quite a demand for such a creature, and where there is demand, eventually there is supply. Turning from this biological wishful thinking back to the world of machinery, the only novel item in the very short range category is the conveyor. By this, I mean all continuously moving systems such as escalators, or the moving ways described by H.G. Wells in The Sleeper Wakes. A few small-scale experiments in pedestrian conveyor systems have already been made in New York and London to remove the notorious bottlenecks between Grand Central Station and Times Square, and between the Monument and the Bank. A sane city, designed from the ground up for the convenience of its inhabitants, would be crisscrossed with slowly moving pavements at different levels. Perhaps the north-south ones would be on even levels, the east-west ones on the odd, with the frequent changeover points between them. The layout of a conveyor belt city would be somewhat dull and mechanical for obvious engineering reasons, though it need not be as monotonously rectilinear as Manhattan. I suspect that the greatest difficulties in the way of its realization would not be technical or economic, but social. The idea of free public transport, though it makes a good common sense, will be anathema to a great many people. Already I can picture the violent campaign the taxi drivers union would launch in favor of rugged individualism against the horrors of socialized transportation. Yet it is becoming obvious that vehicles, except public utility ones, cannot be permitted much longer in urban areas. We have taken some time to face this fact. More than 2,000 years have passed since increasing traffic congestion in Rome compelled Julius Caesar to ban all wheeled vehicles during the hours of daylight, and the situation has become slightly worse since 46 BC. If private cars are to continue to operate inside the cities, we will have to put all the buildings on stilts so that the entire ground area can be used for highways and parking lots, and even this may not solve the problem. Though it seems unlikely that pedestrian conveyors will ever be used except over short distances, there is some possibility that they may have wider applications. About 30 years ago, in a short story, The Roads Must Roll, Robert Heinlein suggested that travel even over considerable distances would one day be based on the conveyor belt system, if only because of the mounting carnage of the petrol war ruling out the continued use of automobiles. Heinlein developed, in his usual meticulous detail, both the sociology and the technology of the rolling road culture. He imagined vast multi-strip highways, with central express sections traveling at 100 miles per hour, complete with dining places and restrooms. The engineering problems of such a system would be enormous, but not insuperable. They could be hardly compared with those overcome in the development of nuclear weapons, though the capital sums involved would be even greater. It is my own feeling, however, that the mechanical difficulties would be so serious that their solution, in terms of present-day technology, would not be worth the trouble. Heinlein himself was careful to point out that what might happen if a high-speed belt snapped with a few thousand passengers aboard it. The fundamental problem of continuously moving pedestrian conveyors is how do you get onto them safely? Anyone who has observed a nervous old lady hovering on the brink of an escalator will appreciate this point, and I do not think that we can expect ordinary members of the public, possibly loaded down with shopping or infants, to cope with speed differentials of over 5 miles per hour. This means that a large number of adjacent bands will be required if we hope to build expressways traveling at 50 or more miles an hour at their center. The ideal moving road would be one that had a smoothly increasing speed gradient from edge to center, so that there were no sudden jumps in velocity. No solid material can behave in this matter, and at first sight the concept appears to be physically unrealizable. But is it? The flow of a river exhibits this kind of behavior. Immediately adjacent to the bank, the liquid is motionless. The velocity of the surface layer increases steadily towards the middle, falling off again towards the other bank. You can prove this by dropping a line of corks across a uniformly flowing river. The line will quickly bow into a curve, as the corks in the center move ahead of those at the edge. Nature has provided the prototype of the perfect moving way for those small insects that can walk on water. In one of my earlier novels, I suggested, not very seriously, that we might someday invent or develop a material that would be sufficiently solid in the vertical direction to support the weight of a man, yet fluid enough in the horizontal plane to allow it to move at variable speeds. A great many substances are in some degree anistropic. anisotropic. That is to say, their properties vary at different directions. The classic example is wood. As every carpenter knows, its behavior along the grain is completely different from that at right angles to it. Perhaps local electric, magnetic, or other fields, acting on powders or dense liquids, might produce the desired anisotropic effect. Remember what happens to iron filings in the presence of a magnetic field. What I'm trying to visualize, and I must admit that this is hopeful whistling in the technological dark, is a fairly thin layer of substance X supported on a fixed solid base within which the necessary polarizing fields are generated. These fields give X its rigidity in the vertical direction and also impart the desired velocity gradient across the strip. You can step onto the edge with perfect confidence because it is almost stationary. But if you walk towards the center, you will experience a smooth and steady increase in speed until you reach the express section. There would be no sudden jumps, as is inevitable with any system of parallel belts. A continuous speed variation right across the road would be quite annoying. It would be impossible to stand still, for one foot would creep ahead of the other. The solution would be to have a fairly wide uniform velocity bands, which might be marked out by colored lighting, separated by narrow transition strips where the speed increased rapidly but smoothly. The bands could be easily varied in width and direction according to the flow of traffic, merely by altering the pattern of the field that produced them. At the end of the road, the field would be switched off. Substance X would revert to a normal, well-behaved liquid or powder and could be pumped back to the beginning of the circuit through pipelines. The whole concept is so beautiful, and such an improvement on the conventional scheme of moving belts, that it will be a great pity if it turns out to be totally impossible. On the other hand, there might be more advanced solutions to the problem of pedestrian traffic. If we ever discover a method of controlling gravity, a possibility to be discussed in more detail in Chapter 5, that will give us much greater powers than the neutralization of weight. We will be able to produce not only levitation, but guided movement in any desired direction, up or down, horizontally or vertically. Because our generation has already known the weightlessness of sea and space, we should not find it completely fantastic the picture of a city full of effortlessly floating pedestrians, if one can call them that. It is a little hair-raising, though, to realize what vertical transportation would imply in a structure the size of the Empire State Building. There would be no elevator cages, just plain shafts, straight up and down for 1,000 feet. But to their occupants, under the influence of a gravity field that has been artificially twisted through 90 degrees, they would appear to be horizontal tunnels, along which they were being swept like thistledown before a gentle breeze. Only if the power failed would they come back to reality with, if you will pardon the metaphor, a bump. It is obvious that anyone from our age would not last for long, physically or psychologically, inside such a city. But how long would a man from 1800 survive in one of ours? Even if they are banned from the city, motor vehicles are likely to dominate the short 10 to 100 mile range of transportation for a long time to come. There are few men now alive who can remember that it was otherwise. The automobile is so much a part of our existence that it seems hard to believe that it is a child of our century. Looked at dispassionately, it is an incredible device, which no sane society would tolerate. If anyone before 1900 could have seen the approaches to a modern city on a Monday morning or a Friday evening, he might have imagined that he was in hell, and he would not be so far wrong. Here we have a situation in which millions of vehicles, each a miracle, often unnecessary complication, are hurtling in all directions under the impulse of anything up to 200 horsepower. Many of them are the size of small houses and contain a couple of tons of sophisticated alloys, yet often carry a single passenger. They can travel at 100 miles per hour, but are lucky if they average 20. In one lifetime, they have consumed more irreplaceable fuel than has been used in the whole previous history of mankind. The roads to support them, inadequate though they are, cost as much as a small war. The analogy is a good one, for the casualties are on the same scale. Yet despite the appalling expense in spiritual as well as material values, look what Detroit has done to aesthetics, our civilization could not survive for 10 minutes without the automobile. Though it can obviously be improved, it seems hard to believe that it can be replaced by anything fundamentally different. The world has moved on wheels for 6,000 years, and there is an unbroken sequence from the ox cart to the Cadillac. Yet one day, that sequence will be broken, perhaps by ground effect vehicles riding on air blasts, perhaps by gravity control, perhaps by still more revolutionary means. I shall discuss these possibilities elsewhere. Meanwhile, let us take a brief glance at the future of the automobile as we know it. It will become much lighter, and hence more efficient, as materials improve. Its complicated and toxic petrol engine, which has probably killed as many people by air pollution as by direct physical impact, will be replaced by clean and silent electric motors, built into the wheels themselves and so wasting no body space. This implies, of course, the development of a really compact and lightweight method of storing or producing electricity, at least an order of magnitude better than our present clumsy batteries. Such an invention has been overdue for about 50 years. It may be made possible either through improvements in fuel cells or as a byproduct of solid-state physics. These improvements, however, will be much less important than the fact that the automobile of the day after tomorrow will not be driven by its owner, but by itself. Indeed, it may one day be a serious offense to drive an automobile on a public highway. I would not care to say how long it will take to introduce completely computerized motoring, but dozens of techniques already developed by airlines and railroads already point the way to it. Automatic blocks, electronic road signs, radar obstacle detectors, navigational grids. Even today, we can visualize the basic elements required. An automatic highway system will, of course, be fabulously expensive to install and maintain, but in the long run, it will be much cheaper in terms of time, frustration, and human lives than the manual present one. The automobile of the future will really live up to the first half of its name. You need merely tell it your destination by dialing a code or perhaps even verbally, and it will travel there by the most efficient route, after first checking with the highway information system for blockages and traffic jams. As a mere incidental, this would virtually solve the parking problem. Once your car had delivered you at the office, you would instruct it to head out of town again. It would then report for duty in the evening when summoned by radio or at a pre-arranged time. This is only one of the advantages of having a built-in chauffeur. Some people I know enjoy driving, for reasons which are simple and Freudian, though none the worse for that. Their desires could easily be fulfilled at suitable times and places, but not on the public highways. For my own part, I steadfastly refuse to have anything to do with vehicles in which I cannot read when I am traveling. It is therefore impossible for me to own a car. At this early stage in its technical development, a car would own me. The most revolutionary, indeed from the viewpoint of our grandfathers, the most incredible, even in the history of transport, has been the rise of aviation. Eventually, all passenger traffic will go by air when the stage lengths of more than a couple 100 miles are concerned. The railroads recognize this, as is proved by their often unconcealed efforts to discourage customers. They would much prefer to concentrate on freight, which is more profitable and far less troublesome, for it is seldom in a frantic hurry and does not object to being parked in sidings for a few hours, nor does it insist that its feet be warmed and its martinis chilled, vide Peter Arno's famous cartoon. The story of the railroads, which have served mankind so well for almost a century and a half, is now entering its final chapter. As industry becomes decentralized, as the use for coal for fuel diminishes and nuclear power enables the factories to move nearer to their sources of supply, so the very need for shifting megatons of raw materials over thousands of miles will dwindle away. With it will pass the chief function of the railroad, which has always been the moving of freight, not of passengers. Already, some young countries, Australia for example, have virtually bypassed the railroad age and are building transportation systems based on highways and airlines. In a few more decades, today's Pullmans and diners and roomettes will be as much period pieces as the Mississippi paddle boats and will evoke equal nostalgia. Nevertheless, by a strange paradox, it is quite possible that the heroic age of railroads still lies ahead. On airless worlds like the Moon, Mercury, and the satellites of the giant planets, alternative forms of transports may be impractical, and the absence of atmosphere will permit very high speeds, even at ground level. Such a situation almost demands railroads, using that term to mean any system employing fixed tracks. On rugged, low-gravity worlds, there is a good deal to be said for monorails or cars suspended from overhead cables, which could be slung across valleys and chasms and craters with complete indifference to the geography below them. A century from now, the face of the moon may be covered with such a network, linking together the pressurized cities of the first extraterrestrial colony. Meanwhile, back on Earth, the flow of passenger traffic into the air will still be further accelerated when VTOL, vertical takeoff and landing, aircraft are perfected. Though the helicopter, for all its importance in more specialized fields, has had little effect on public transportation, this will not be true of its successors, the short and medium-range Airbuses of the near future. What form they will take and what principle they will operate on, no one can foresee at the moment, but no one has any doubts that practical versions will soon be developed in some or other of the horrid-looking devices that are now laboriously heaving themselves off the ground, with the aid of jets, rotors, or tilting wings. We will not have conquered the air until we can go straight up and come straight down, and as slowly as we please. As far as intercontinental transportation is concerned, the battle is already over, the decision already made. Where speed is required, the airlines have no competition. Indeed, the ridiculous situation has now been reached where traveling to and from the airport and getting through the paper curtains at either end takes longer than a transatlantic flight. Nevertheless, aircraft speeds will increase very substantially over the next few decades, and such restrictions as exist are economic rather than technological. The airlines have to pay for the current generation of jets and would be most unhappy if suddenly confronted with the supersonic transports they fully expect to be buying in the 1970s. This belief that major advances in performance are still to come is an aftermath of the jet and rocket revolutions of the 1945 to 55 period, when all existing records were so thoroughly shattered that conservatism about the future seemed ludicrous. That was not always the case, as the examples I have given in Chapter 1 demonstrated. I would like to give one more because it is easy to forget how often the views of technical and scientific authorities about future progress fall hopelessly short of the truth. Yet the experts continue to make the same mistakes, and many of them will go through their predictable routines again when these words appear in print. Back in 1929, a leading aeronautical engineer, now well known to you in quite a different connection, I'll give his name in a moment, wrote a paper on the future of aviation, which opened with the words, "The forecast is freely made that within a few years, passenger-carrying aeroplanes will be traveling at over 300 miles per hour, the speed record today." This, he stated pontifically, was gross journalistic exaggeration, as the commercial airplane will have a definite range of development ahead of it, beyond which no further advance can be anticipated. Here are the advances this far-sighted prophet anticipated, when the aeroplane had reached the limit of its development, probably by the year 1980. Speed, 110 to 130 miles per hour. Range, 600 miles. Payload, 4 tons. Total weight, 20 tons. Well, every one of these figures had been multiplied by more than 5 by the time their proponent had died in 1960, mourned by thousands of readers in many countries. For in 1929, he was N.S. Norway, chief calculator on the R-100 airship design, but in 1960 he was famous as Neville Shute. One only can hope, as he himself must have done, that On the Beach turns out to be as wide off the mark as this earlier and lesser-known prediction. Even the earliest versions of the Concorde demonstrated that we can build conventional jet transports operating at speeds of 1,000 or 2,000 miles an hour. This would mean that no journey on Earth could last for more than 6 hours, and very few would be over 2 or 3 hours duration. A worldwide pattern of long-distance mass transportation might develop, far more like today's bus and rail services than anything now offered by the airlines. Meals and stewardesses would be as inappropriate as on the IRT or the London Underground. The analogy may be all too close, for some operators have suggested that ultra-cheap air couches could be run on a standing room-only basis. Those who have already experienced the joys of a transatlantic economy flight in the company of a dozen bilious babies may be glad to know that the future has yet deeper delights in store. In the face of competition from the air, the shipping lines have been wisely concentrated on selling comfort and leisure. Although on most routes, most passengers now travel by air rather than sea, this traffic has not all been won at the expense of ocean liners. Indeed, there has been, at least in Europe, a major building program which has seen the launching of such magnificent ships as Oriana, Leonardo da Vinci, and Canberra. Some of these are pure passenger vessels, that is, they do not rely on freight for any part of their income. Whatever the future brings, such ships will continue to ply the ocean for as long as men remain men and feel the call of their ancient home, the sea. The end of the freight-carrying ship, the tramps and the windjammers and the galleons and the quinquiremes for 6,000 years have carried the cargoes of the world, is already in sight. In another century, only a few will be left as picturesque survivals in out-of-the-way places. After ages without a rival, the cargo ship is now challenged simultaneously on 3 fronts. One challenge is from below the water. The submarine is a much more efficient vehicle than the surface ship, which wastes much of its energy on the production of waves. With the advent of nuclear energy, the high-speed, long-range submarine envisaged years ago by Jules Verne is at last practical, but so far has been developed only for military purposes. Whether the heavy initial cost and the problems of underwater operation will make the cargo submarine economical is another question. An interesting compromise, which almost certainly is economical, is the flexible towed container, now being developed in the United Kingdom for liquid cargoes. These giant plastic sausages, which can be rolled up and shipped, or even flown cheaply from point to point when they are not in use, have now been built in lengths of up to 200 feet, and there is no obvious limit to size. Since they can be towed completely submerged, they have the efficiency of the submarine without its mechanical and navigational complications, and they can be built very lightly and cheaply, since their structural strength is extremely low. Unlike rigid ships, they do not resist waves, but give with them. They will even kink at sharp angles when their tug makes an abrupt turn. With commendable honesty, the inventor of the Dracone, the trade name for the flexible submarine tanker, has admitted, "I got the idea from a science fiction story." This was presumably Frank Herbert's excellent novel The Dragon in the Sea, which dealt with a hair-raising wartime voyage by an atomic submarine towing a string of submersible oil barges. It is, indeed, as oil tankers that such vessels may have their greatest use. Petroleum products constitute half of the world's total of goods moved by sea, now running at about 1 billion tons a year. Certain Greek ship owners may well view with apprehension the replacement of their beautiful tankers by overgrown plastic bottles. Other bulk cargoes, grain, coal, minerals, and raw materials generally, could be carried in the same manner. For most of these cases, speed is not important. What matters is that a continuous flow be maintained. Where speed is vital, air freight will be used for all except the bulkiest cargoes, and one day even for these. Air transport is just at the beginning of its evolution. To set limits to where it may become would be folly, as the examples I have quoted clearly show. Though less than 0.1% of today's freight travels by air, the time may come when it will all do so. Some of it may fly thousands of feet into the sky, but some, and perhaps most of it, may rise only a few inches above the ground. For the nemesis of the ocean-going freighter may not be the submarine or the aeroplane, but the ground effect machine, riding on curtains of air over land and sea. This novel and quite unexpected development may be important, and not only in itself, but as a pointer to the future. For the first time, it allows us to float really heavy loads in the air. This may or may not revolutionize transport, but it will certainly set men thinking seriously about genuine gravity control, one rather trivial application of which I have already mentioned. Gravity control, anti-gravity, as the science fiction writers call it, may prove to be impossible, but the ground effect machine is already here. Now let us see what it and its hypothetical successor may do to our civilization. And it's live.